So thanks for inviting me to give this lecture here today, and I'll be telling you about simulating the world of atoms, molecules, and materials. And this is, as you know, a lecture in this series about the third quantum revolution. And I guess the third quantum revolution is really the revolution associated with the emergence of quantum computing. But before I talk about simulating the world of atoms, molecules, and materials using quantum computers, I should first really tell you a little bit about how we carry out simulations of matter using the computers that we have today, which are classical computers. And so this will be sort of the first part of the talk. And then I will move on to say, how things change now that quantum computers are becoming available, and what, if any, quantum advantage they may bring to this problem. And then finally, very brief at the end of this talk, I will sort of say something about the broader impacts of quantum simulation, the societal impacts of quantum simulation, and how this may change as we become better at simulating different kinds of things. Okay, so first let me talk about sort of the types of things that we're going to simulate. And my background is in chemistry and materials. And so what I'm primarily going to focus on, or what I'm entirely going to focus on, is what I will call ordinary matter. So this is molecules, materials under ordinary human kind of level, or at least reasonably accessible conditions. And matter in this form, molecules and materials under ordinary conditions, they're made of atoms, and then atoms are made of electrons and nuclei, and all these particles are very light, and they're all in very confined spaces, and this means that their behavior is really best described not by Newtonian mechanics, but by the laws of quantum mechanics. And so what this talk is really going to be about is using computers to simulate the behavior of these species of the physical world using these quantum mechanical laws. Now I don't have time, of course, to give a lecture on quantum mechanics, and that's not really the purpose of this talk. But the most important kind of idea that you have to carry in your head is that if you have a set of quantum mechanical objects, if you have a set of, say, n quantum mechanical objects, n atoms or n electrons, and so on and so forth, then the collective behavior of the set of objects is described by a mathematical object known as a wave function. And you can try and describe some sort of interpretation of wave function. People might say, well, it's a bit like a probability, but then it's not really like a probability, and all these sort of complicated things like that. I think the cleanest way to think about it is that it's just some mathematical object, some mathematical thing, and from this wave function, from this mathematical thing, there are some well-defined rules. These are the postulates of quantum mechanics, from which you can extract all the information you want about observations in the system, things you might measure or other things you might be concerned about. So what does this wave function look like? Well, let's say you have a set of n atoms. Okay, then you might think the atoms can be in different positions in space, but somehow in quantum mechanics they're sort of somehow in all positions in space simultaneously. So what the wave function does, it assigns a number, a complex amplitude, we say, to every possible configuration of positions of the atoms. So for wherever you put the atoms, there is some number associated with it. That's what, and this wave function gives you that number. So it's a very high-dimensional function. Looks like a very, very complicated object. Now, sometimes it's a little bit inconvenient to talk about systems where the possibilities involve continuous variables, right? These position is a continuous thing. You can change it, there's an infinite gradations of these things. But a wave function can be used also to describe systems where the objects only have a discrete set of configurations or a discrete set of possibilities. One example of this are what we call spins or spin 1/2 particles. So these are objects, rather than having sort of a continuous set of positions that they can live in, they only have two states. They can either be sort of spinning up or spinning down. And then when you have a wave function for a collection of n spins, then this wave function assigns a complex number to every possible configuration of all the spin ups and spin downs of the n objects. Okay. And so when we're talking about simulating a quantum system, what we're actually doing is that we're trying to represent this mathematical thing, this wave function, on a computer. And there are different kinds of computers you can use, right? So I'm giving this talk on a classical computer, right, something like this. And then, nowadays there are other kinds of quantum devices that you may use. And as I mentioned at the first part of this talk, I'm primarily going to be talking about using classical computers. But in addition to just representing the wave function or storing the wave function on the computer, you also have to solve for its correct form. You can just store. You have to know exactly what values this wave function takes. And so you have to solve some equations to determine the correct values of the wave function. And those equations are Schrödinger's equations. And there's essentially sort of two variations of them. So the first one is an equation you solve if you want to obtain the equilibrium properties of a system. So something like the lowest energy state of a molecule, or low energy state of a material. And then there's this we call the time-independent Schrödinger equation. And then there's a second sort of Schrödinger equation, slightly more general one, which tells you about the non-equilibrium or dynamical properties of a quantum system. And we call this the time-dependent Schrödinger equation. OK. So we're going to think about putting a wave function computer and then trying to solve for it in some way. And in any such computational task, or in any computational task, you're often interested in how expensive the computation is going to be. So you may be interested, for example, in how long you need to run to carry out the calculation, or perhaps how much memory you need, how much storage you need to store the results or the intermediate data. So talking about the cost of a computation, well, this is what we call complexity. And the theory of complexity is really a branch of theoretical computer science. Now, the way in which computer scientists like to think about complexity is they like it to think about the complexity as a function of the input size of the problem. So what do I mean by the input size? Well, it's just, for example, if you're simulating atoms, how many atoms you're going to put in your simulation, right? So we'll call the size of the simulation n, because you think of this as n just being the number of atoms. And the way in which they like to classify complexity is they like to think about sort of problems which are where the complexity or the cost grows in some somewhat moderate way as a function of the input size. So for example, if your simulation cost just grows proportional to the number of atoms, or quadratic or cubic with the number of atoms, these are all polynomials of the input size. And these kind of calculations where you have a polynomial complexity are termed efficient. And efficient here I put in quotes because efficient here is being used in a technical sense. It does not really correspond to the colloquial sense of efficient, as I'll explain in a minute. And then another common category of problems are ones where if you just change the problem size a little bit, for example, you just add one more atom to the simulation, then the cost just sort of blows up immediately and you cannot do it. Okay, so those kinds of problems are where you have an exponential dependence of the cost on the problem size. And we call these exponentially hard problems. Hard, that's the technical term. So as I just mentioned, when I say that polynomial calculations are efficient, it just means that the theoretical cost is not too high, but they still may be impractical to run. So for example, if you had some kind of complexity here, which was n to the power of 100, then it would still mean that if you change the problem size a little bit, the cost would grow extremely rapidly. But the point is that the usefulness of this distinction is that if you think that computer power itself is growing, which it has been over many, many decades, then if you have these polynomial cost problems, then eventually, if you wait for some number of decades, there will eventually be something that you can run. But if you have an exponentially hard problem, then in essence, the growth and complexity of the problem will sort of outstrip the growth in computing power, even over some period of time. And so they'll always be very hard to run. And so that's why this is a sort of useful distinction. OK, so with those sort of preliminaries out of the way, we can now talk about the classical cost of doing a quantum simulation, or the classical complexity. So as I mentioned, we have to represent the wave function on a quantum computer. And the wave function is this very high-dimensional object, which carries an exponential set of numbers in them. And so consequently, you see that just the storage cost of putting the wave function on a computer is already exponentially large. Okay, it's exponentially hard, okay, which is not very good. And And then the second thing is, as I said, you don't only just store some wave function, you have to sort of compute the correct one, so you have to solve these Schrödinger equations. And solving for the wave function, which is this exponentially large object, and manipulating all that data must also be of some kind of exponential cost. So that's all a little bit discouraging, right? So you see that sort of storing the wave function or computing the wave function seems like it's going to be very, very difficult. And your mind might immediately turn to whether there are any loopholes, right? You might say, well, okay, but I really want to make progress, so well, maybe I don't need to actually store these numbers, maybe there's some special structure, or maybe we don't need all this information to just predict some simple property that, like, is this something stable? Maybe you don't need all these details. But the inescapable fact is that if you don't make any assumptions at all, simulating quantum systems is formally exponentially hard on a classical computer. And so that's sort of the essential rub of quantum mechanics, which was recognized already very early on by the originators of the theory, the original founding scientists of the theory, namely that, as stated by Dirac, and you've heard this quote already, namely that even though we know the laws that govern most of physics and all of chemistry, we can write the equations down that govern the world, somehow extracting information from these equations appears to be very, very difficult. And so this is what sort of Dirac wrote down, 100 years ago. Now, of course, at the time, Dirac wasn't really thinking about complexity theory, and he certainly didn't know anything about computers because they didn't exist at the time. But he already identified this essential difficulty that quantum simulation, without any assumptions, is sort of a impossible task. But what the past 100 years have taught us, however, is something very different, because we have managed to, as a scientific community, extract enormous amounts of information out of quantum mechanics and say very concrete things about the world by solving the quantum mechanical equations. And the reason, and the way in which this has been achieved has been through the combination of both insights into these mathematical functions, the wave functions, and the development of algorithms which take advantage of these insights to produce concrete results. And so that's what I'm going to tell you about in the next few slides. Okay, so what is it that makes quantum simulations on classical computers possible? There's essentially these three things. The first is that there have been many insights into the mathematical form of these wave functions for physically relevant problems. This is sort of the theory of quantum phases, which is sort of a branch, I guess, of condensed matter theory and some other areas of physics. Then secondly, there's been the development of algorithms that use this additional information, so you're no longer running a simulation without assumptions. You're going to make some assumptions, but you're going to use this additional information about how nature behaves in the world around you to efficiently carry out computations. So these algorithms are not fully general. They're what we call heuristics because they use some assumptions. But if these assumptions are the correct ones, they are incredibly powerful. And they're developed in many disciplines, for example, in chemistry, condensed matter theory, and quantum information theory. And then finally, of course, the last thing that has changed the situation has been this rapid growth and availability of computers. But I want to stress that although, if you come as an outsider to the entire field, you might think that computational quantum science is just entirely about using computers to do things, and it's just because we have computers that we can do things. That's not actually the situation. As I was saying, if you don't have any insight into the structure of quantum mechanics, simulating it is exponentially hard, and that hardness sort of outpaces the growth of computing power. So it's really what has really been the game changer is these first two things, right? The insights into the qualitative behavior of quantum systems and the development of algorithms that use these insights, not just this brute force computing power. And so that's why I'll be spending my time talking about these first 2 points. Okay, so what do I mean by insights into the qualitative behavior of physical systems? Well, if you look at this wave function, it's this exponentially complicated thing. And so you imagine that potentially, if you look at the world around you, the possible behaviors of physical objects, there should be sort of some exponentially large set of possibilities that you see. But what you actually see is that in just ordinary matter and ordinary materials, the categories of behaviors that you find, physical behaviors that you find, are actually relatively limited. So what we understand is that if you look at the low energy or the ground states or lowest energy states of materials, they can be classified into these different discrete categories that we call phases. And phases are sort of just like you're familiar with from sort of elementary school, right? So you have solids, liquids, and gases, right? These are sort of classical phases of matter. The phases that you see for quantum matter, they're a bit richer, there are more possibilities, but there still isn't this sort of exponentially large number of possibilities. Okay, so if we look at quantum objects, we see that they might be, for example, insulating materials or metals or superconductors or various types of electronic crystals or topological states and so on and so forth. And it's very rich, the number of phases that we see, but it's not sort of exponentially rich. So you don't see this dizzying array of possibilities. So that's one fascinating thing. And then the second fascinating thing is that in each of these cases, condensed matter physicists have found that they can write down, really sort of almost in pencil and paper, very simple qualitative mathematical wave functions that describe the behavior, at least the qualitative behavior of materials in those phases. Okay, so you can write down simple theories of metals and simple theories of superconductors, and so on and so forth. Now, why this is slightly mysterious, but this just seems to be the way that the world works, and we can discuss the why later, I suppose. But the take-home message about this is, rather than being this completely mystical and non-understandable kind of physical theory, we find that, at least in the natural world, the quantum wave functions that we see are often very understandable, and there doesn't really seem to be an exponentially large number of different qualitative behaviors. So this is a very big simplification. Okay. So the second key factor is that if we assume what I just said is true, okay, so assuming physical states really fall into some kinds of understandable phases, then nature really kind of looks a little bit like this, right? So this is sort of the set of possibilities of behaviors of physical systems, and somehow they just fall into different categories, so these different kind of regions are different phases. And we know from the developments of condensed matter theory that there are these simple mathematical wave functions we can write down to describe at least qualitative behavior in each of these phases. And if we now have this setup, then one can begin thinking about a quantitative computational theory of not just this very simple point in the phase space, but sort of a little bit away from it. And so essentially, the way in which many computational algorithms work is they start from this qualitatively correct description of the wave function, and they sort of just nudge it and push it so that you can describe quantitatively the materials in this region of the phase space. So that's the basis of many, many successful algorithms. And the sort of empirical experience is that moving away from this point is not computationally so hard. I mean, you have to do some computation, but it's not exponentially hard. Another common approach, which is a little bit more, nowadays you might describe this as more machine learning approach, is you say that you can compute all the properties that you're interested in this simple, analytically understandable point, or very simple, qualitatively correct point, and then perhaps you can learn a map from the numbers you're computing to the precise numbers you want of the material that you're interested in. And this type of thinking is the basis of a very popular type of simulation method known as density functional theory. But the essential point is that these types of heuristic algorithms, which use this additional physical understanding, can be formulated. And because we're not really blindly exploring this exponential set of possibilities, they can be very efficient. Okay, so the take-home message here is that quantum simulations actually, with classical computers, actually become possible because the states that we observe in normal physical systems are surprisingly quite restricted. And sometimes this is described in the following picture, that there's this vast set of possibilities, but physical states only live in some small corner that you call this physical corner of the Hilbert space, or the space of quantum possibilities. Okay, So what can you do with all these techniques? And these insights. So as it turns out, you can simulate many types of problems with some degree of accuracy, and in many cases, accuracy that is very useful. So just to run through a few quick examples, if you are talking about very small molecules which only have a few atoms, then you can solve the equation, the Schrödinger equation, very, very accurately, and in fact to an accuracy that often rivals the best measurements you can take experimentally. In some cases, perhaps even better than an experimentalist can measure it. In this case, you can see you're really fulfilling the potential of quantum mechanics as a predictive theory. If you move up a scale into systems of, say, hundreds of atoms or larger, so getting into, say, biologically interesting molecules, there you can't reach quite the same accuracy, but you can still typically solve things to a point where you can say what the mechanism of reaction is, exactly sort of what pathway atoms will combine and bonds are broken, and say qualitatively something about, say, the rates of these types of processes. And then finally, if we go to sort of very, very complex problems, like quantum materials or strongly correlated electronic problems, in that case, it's quite difficult to say something that's qualitatively very precise. But nowadays, it is possible often to say qualitative things about these more exotic phenomena. For example, it's becoming possible in the theory of high-temperature superconductors to say something about where the material trends come from in the observed superconducting temperatures. Okay, but despite all these successes, this doesn't mean everything can be done, and there remain many challenges. And you'll have noticed that in the way I was describing, how well we can simulate things, I was distinguishing different classes of problems by sort of the accuracy you can reach. And as it turns out, it is quite hard to increase the accuracy beyond a certain point, often in a classical simulation. So in these correlated materials, I mentioned that we can obtain some qualitative information, but really nailing down the precise behavior with multiple decimal points is extremely, extremely difficult. As it turns out, how difficult it is to increase the accuracy of a classical simulation, a classical heuristic method, is in fact something that's very poorly understood. It's something that there's a little bit of data on. It's something that I've studied a little bit in recent years. But roughly speaking, it appears that if we want to obtain some precision in our answer, then the cost to improve the cost to obtain that given precision is some type of polynomial in the inverse precision. So for example, if I want to lower the error by a factor of 10, okay, then the 1 over a factor of 10 is 10, and this would be a polynomial of 10. Now notice there's no exponential here, okay? So it's not, in a formal computer science sense, it doesn't seem to be truly hard to improve the precision. But this polynomial can, in many cases, be a very high polynomial. And so in practice, it can be very difficult to obtain high accuracy. So the summary is that heuristic algorithms are in many ways incredibly successful, far more successful than you would have imagined from Dirac's original statement, but obtaining high precision remains a bottleneck. Okay, so that brings me now to the second part of the talk, which is to talk about what happens when we have quantum computers. Okay, so again, I can't really talk exactly about how quantum computers work and how quantum algorithms work, but the only essential point you have to recognize is that quantum computers are devices that both store the information and manipulate the information essentially inside the wave function of the computer itself. Okay, so, and the fact that if you allowed yourself this computational paradigm where you can do computation using the wave function of the computer itself, the fact that this would be perhaps very interesting for quantum simulation was, of course, recognized by Feynman in the 80s and has been proposed as a new paradigm for many things, but quantum simulation is one of the most important things that quantum computers have been proposed for. Now you can see that they might be interesting devices if we again just think about the complexity of doing things. And if we think about the basic task of quantum simulation as first being storing the wave function, then manipulating it, well, we see that if we're going to store the wave function of some physical system, which is these exponential set of numbers, inside the quantum computer, we can actually store it directly inside the wave function of the quantum computer itself, which also can encode an exponential set of possibilities. And so as far as storage is concerned, we're just mapping an exponential number of amplitudes onto the exponential number of amplitudes of the quantum computer, and so there isn't really any exponential storage problem. Okay, so quantum computers can represent these exponential number of amplitudes just with a linear number of so-called qubits. So it solves one of the problems of quantum simulation, which is namely how you store your results. But there's, of course, the fact that you need to compute the correct wave function in the first place, and you still need to use a quantum computer to solve these equations. And this is a more subtle question of how difficult it is to solve these equations on a quantum computer, and that's really the domain of quantum algorithms for the simulation problem. So when we're thinking about quantum algorithms for quantum simulations, we often like to think about them relative to some classical algorithm because we want to understand if we're going to get any quantum advantage from using a quantum computer. And one can define sort of a quantum speedup as being some ratio of cost, like the ratio of the classical cost for solving something over the quantum cost. And one can imagine this ratio taking different forms, right? So you can imagine there being some gigantic speedup where if you make your problem larger and larger, the quantum computer just zooms past the classical computer in speed, right? This would be some kind of exponential speedup. Or you can think of a more modest speedup, some kind of polynomial in the system size. Or there might just be some constant speedup, or there could be no speedup at all, of course. Right? Now, in our daily lives, actually constant speedup's pretty good, right? So like if I said my phone's 10 times faster than your phone, that's quite good, right? But in this realm, however, people generally don't focus on this end of the spectrum, but mainly on this top end of the spectrum, like exponential speedup. And the reason for this is because, relative to classical devices, quantum computing devices are very, very complicated. And the overhead of quantum computing is very, very large. So, for example, if we think about just a basic operation of a quantum computer, a quantum gate, then under really very optimistic assumptions, you might expect a quantum gate with error correction to execute in, say, a millisecond of time. But if you think about a classical logic gate on a normal device, it executes on the 10 to the minus 9 seconds on a nanosecond time scale. And then another difference is that classical computers are much easier to build than quantum computers, and so we have a lot more of them. It's much easier to make lots and lots of classical chips than it is to make quantum chips. And so it's much easier to take advantage of parallelism in classical computers, right? So if you just take a GPU card, it has, in fact, many thousands of computational cores on it already. And so if you combine this sort of classical parallelism advantage of classical computers with the advantage in the gate speed, then you have this overhead of, say, 10 to the 9 to 10 to the 12, which a quantum computer has to beat. Okay. And so in this case, if you have just a constant speed up, even if it were 100 times, it's not going to beat this overhead. And so for this reason, most people try to think about whether or not they can get exponential speed up on a quantum computer with a quantum algorithm, because it essentially would eventually negate any of this overhead. Okay. So now let's look at some quantum algorithms and how they might perform and what advantages they might have for different types of physical simulations. So let's again first start. Let's first start with the task of sort of equilibrium simulation or ground state simulations. So we're solving the time-independent Schrödinger equation. And the way in which a quantum computer would solve this is that you prepare some input to the quantum computer. So you prepare your wave function of some form, okay? And this wave function will, in general, be a superposition of many different energy states of the molecule or the material. And let's say you're just interested in just the ground state. then what you would do is you would try and measure the energy of the basically of the quantum computer. And the measurement of some property in quantum mechanics collapses this superposition of states just into one state. So your original input state is a superposition of many ng states, but after measurement, it collapses just into one of them. And it might collapse to the lowest one, which I've denoted 0, or the next lowest one, which I've denoted 1, or the next lowest one, which I've denoted 2. And the probability of obtaining the ground state, the probability of success of this algorithm, depends on how well you prepared your initial state, how large this coefficient is. So the key to having a very efficient quantum algorithm is to ensure that the probability of success is very high. And so consequently, to understand if you have some large quantum advantage, like an exponential quantum advantage, you have to understand whether you can prepare states efficiently with a very large coefficient here in cases when the corresponding classical algorithms are very inefficient. So that leads us to the question, are there in fact problems where it's very easy to prepare good input quantum state, but where all the classical algorithms we know are very, very hard, and so consequently you'd have a very large quantum advantage. So how do I sort of prepare a good state for a quantum computer? Well, as it turns out, to prepare a good approximation to the ground state of a quantum computer, you also need to know something about the solution you're trying to obtain. I mean, after you're trying to prepare a specific state, so you need to know something about it. And if I take one pretty standard preparation strategy in quantum computers, known as adiabatic state preparation, it works like this. So essentially, you just prepare some very, very simple state that you just know how to dial into your quantum computer, and then you just slowly nudge from that position to the correct state that you want to have a very large component of your ground state in. But the problem with this procedure is that if you prepare a state that has the incorrect qualitative form, so let's say you start in the wrong phase, then in this process of nudging towards the correct state, you find that you encounter an obstruction. And in fact, this preparation process can, without any additional information, take an infinitely long time. So the situation is really as follows. I mean, for most of the things that we want to simulate, we know that they just fall into these standard phases. And we have actually quite good qualitative information on what those phases are. And so consequently, preparing the quantum state on a quantum computer, a good initial guess, is not a difficult task. But at the same time, for all these phases, we actually have because we have a good classical understanding, I've been arguing in the first part of the talk that the classical simulations are then also efficient. So to obtain a very large quantum advantage, you either need two things to happen. Okay? So you either need this early assumption that if you know what phase you're in, that classical simulations are efficient. You need this basic assumption to break down. Or you have to have some intrinsically quantum phases and materials for which there's no simple classical description at all. That would be very odd, because that, I think, sort of goes against how theoretical condensed matter physics works, right? If you're trying to formulate any theory, on a pencil and paper, you're sort of implicitly assuming that you can write down some kind of classically understandable description. But perhaps it's possible there are phases for which no such simple description exists. So to date, I'm not aware of any evidence for either of these breakdowns. And so this is the basis for arguing that there isn't, in fact, any evidence that you can get an exponential speedup in ground state simulation of ordinary molecules and materials. Nonetheless, there is evidence that polynomial speedups are quite likely. And the reason is, again, about this problem of precision in classical simulations. So I already argued that in the classical simulations and classical algorithms we know today, if you want to increase the precision, the cost that you need is sort of some polynomial in this inverse precision. But in a quantum system, in sort of the ideal quantum algorithm, the precision you get in an energy estimate is just given essentially by the uncertainty principle. So if you simulate for some length of time, then you can get some precision, which is 1 over that length of time. So that means the cost to obtain some given precision is just 1 over the precision. And so you see there's an immediate polynomial factor here. And so you'd expect there should be some type of polynomial quantum speedup. In the literature and in most of the science, most of the time people turn their nose up at polynomial speedups. But I think at least for ground state simulation, exponential speedups are very unlikely. And so characterizing this polynomial speedup better is, I think, very important. OK. I'll very briefly now talk about simulating not just ground state and equilibrium problems, but simulating dynamical problems on the quantum computer. So to simulate a dynamical problem, you have to solve the time-dependent Schrödinger equation. And in fact, so long as you can prepare the initial state for your dynamical process, then one knows, in fact, that quantum simulation on the quantum computer of this time-dependent Schrödinger equation is, in fact, always something you can carry out efficiently. It's always a polynomial cost. And at the same time, we know that without any assumptions, the simulation of quantum dynamics on a classical computer is always exponentially hard. And so this then raises the question, does it mean that the quantum simulation of dynamics on quantum computers is always exponentially faster than a classical computer? So I have to say that we don't know the answer to this because it's possible there are some loopholes that classical heuristics could take advantage of. But in some general sense, we're still at a very early stage with respect to understanding the power of classical heuristics in quantum dynamics. But as some sort of illustrated story of the potential of classical heuristics, I'll talk about a recent experiment. So for very recently, there's an experiment carried out on a large quantum computer, which was the IBM Eagle device, which has 127 qubits. And people carried out a simulation using all the qubits. So it doesn't really matter exactly what they did, but they carried out some kind of quantum dynamics using all the qubits and running the dynamics for quite some time using sort of lots and lots of quantum gates. And one of the arguments in that paper was that we know that the quantum computing simulation of dynamics should be efficient, and using classical algorithms, it's not clear that it's ever efficient. So presumably, the quantum computer should be able to do things better than the classical computer in this case. And there was some evidence presented that this was the case, right? So this is a graph taken from the paper where on the quantum computer, they computed these blue dots, and then using some classical heuristic algorithms, they compute these other lines. And these lines don't clearly match up with the blue dots. And so it seemed indeed that a quantum computer in this case was demonstrating its usefulness in simulating quantum dynamics. But what happened after this paper appeared was that, of course, people decided that they should just improve their classical heuristics. And so very quickly, a number of groups, including at the Flatiron, right, including my group and several other groups around the world, showed that it's in fact very easy to simulate the dynamics that we just saw. Right? And not only can you simulate it very easily, you can simulate it far more efficiently, far more accurately than the quantum computer managed to do in that particular experiment. Okay, so this is not meant to be bashing like the progress in quantum computing and quantum algorithms. It's very impressive that these experiments can be done. But what it's meant to show is that we still don't really know what the power is of classical heuristics for the quantum dynamics problem. And so consequently, it's very hard to talk about, at this point in time, about what type of quantum advantage we can expect. Okay. So I think one of the interesting questions one can ask when we're thinking about quantum advantage in quantum simulations is we can ask, well, what should we expect in the future, right? Should we expect quantum advantage to be sort of ubiquitous? So in other words, whenever you have a quantum simulation, you should use a quantum computer, and it's always going to give you a speed up. Or should we think of it as being very fine-tuned, something very highly specialized? So just like the Large Hadron Collider, right? You only use it for very specialized things, right? But for those special problems, it's an incredibly important device. And I don't know the answer to the question, but I think this is something that we will begin to understand in the years to come. So that kind of leads me to the final few slides of my talk, which are about these broader impacts of quantum simulation. So, quantum simulations of atoms and molecules and materials are something that's very well established in sort of society already. Okay, so certainly in academia, we do this. In chemistry departments, people are doing this all the time. In physics departments, people are doing this all the time. But in industry as well. Okay, so for example, in the materials industry, in the pharma industry, people are carrying out these simulations all the time. So they have an important place already in the workflow of the world. But it's often argued that now that quantum computers are on the scene, they will transform society. Whatever that precisely means, okay, but they somehow have a very big impact on society. And one of the ways in which they'll transform society is because that they can simulate things extremely well. Okay? And so we can ask, in what sense is this true now, and in what sense is this potentially true in the future? So we can take one particular industrial example as, just to discuss things. And so one can take the process of drug discovery. So the process of finding a new drug is a very, very long, drawn-out process. It's usually likened to a pipeline, and it starts at the beginning by identifying what your drug should be drugging, typically some protein in the body, and then it goes all the way through many, many stages, all the way through to human trials, for example. And quantum simulations are used today in this process, and they're primarily used in this part here. They're used to estimate, or some approximate version of them is used to estimate how sticky a drug is to the target of choice. So this is known as the binding affinity of the drug. And it's certainly true that the calculations that people do today are very, very approximate. And if you could do them better, you would certainly improve things to some degree. But on the other hand, even if you could compute these binding affinities exactly, and the calculations took 0 time, completely free, this is still only one very small part of the pipeline. There are really many, many, many steps more before you get to a real drug. And the other parts of the pipeline don't really involve any quantum mechanics, right? Like human trials or toxicology and so on and so forth. So essentially, the way that the world is set up today, I think it limits the impact of more accurate quantum simulation. Essentially because the way in which we carry out our experiments or we carry out our industrial processes is really, really non-quantum. If you think about kind of a caricature of chemistry, right, where you just mix some stuff, blast it with a Bunsen burner, and just look at the color, okay, then it doesn't really seem that it doesn't really seem to need the whole quantum wave function to describe that process, right? Okay, so that's appropriate computing, maybe this, or perhaps not even a computer. But if you can imagine a future where you have full quantum control over matter, so the way in which you carry out a reaction is you control the quantum states of every atom, and you manipulate the momentum states, and you bring them together in a reaction. And you do this sort of for all 10 to the 23 molecules. Okay, it's not an easy experiment. Okay. But if you could do this, then you could imagine that to control this type or to design these types of experiments, you really would need better quantum simulations than perhaps a quantum computer. So I think, to say that quantum simulation will transform society, is probably not a realistic statement today. And I think the main reason is because of the way in which we do everything in the world is in a very non-quantum way. But as we achieve more precise quantum control over practically relevant amounts of matter, then indeed quantum simulations, be they quantum or classical, may indeed become truly transformative. And perhaps this will be the 4th quantum revolution. Okay, so let me just finish. So I started, with this statement by Dirac. And I think, it's almost 100 years since these lines are written down. And we can now probably replace these last 3 lines. Okay, so the first point I wanted to say today is that we know the physical laws. And in fact, we can solve them remarkably well because of the insights that scientists have made into quantum systems. And perhaps we may be able to solve them better with a quantum computer, but not always. Okay? This is not such a simple question to answer. And then finally, the impact of this field of science is really proportional to our ability to control and characterize mass at the quantum level, which I think is something that we can look forward to in the future. And so that's the end of my talk. Thank you.
So thank you for a fascinating talk. We have time for some questions.
Yes. Go on.
Oh, does it work? There's one. All right. Thanks for the. Oh. Hold it back. Thanks for the interesting talk. My understanding was that basically what you were saying is that at room temperature, ambient pressure, we have inherently classical fixed points in the universality classes. And if you want to have a quantitative understanding of the vicinity of that fixed point in any universality class, that's basically can be computed classically. Therefore, we understand things about those systems. But I think maybe I misunderstood your argument. Would you agree that still a quantum computer is basically a compute machine with potential of computing a lot of things, not necessarily, protein folding, but also other problems that are inherently NP hard. So ultimately, I think whether or not a quantum computer as a compute machine is useful or not goes back to NP hard versus NP versus NP hard problem, right?
Okay, so there's several statements there. Let me just unpack them. So one is, am I saying that matter under ordinary conditions is not that quantum? And so in some not very precise way, I am saying that. So it seems like things are, otherwise they'd just be completely not understandable. This is kind of my general view. Then about whether quantum computers are useful for things, so even if they are not that quantum, quantum computers can be very useful for simulating them. Okay, so I'm not saying they're not useful for quantum simulations, but then your question is just whether quantum computers are in general useful, and that's I presume so. That's not really my domain, but certainly, there's certainly tasks you can think of which have nothing to do with quantum simulation, like factoring, for which there are well understood quantum algorithms. But then you mentioned the last point about sort of NP hard versus and so on and so forth, and quantum computers exist in a different complexity class from NP hard, and the overlap of this. Generally, it's very hard to prove anything in complexity, but generally, most people would not say that quantum computers can solve NP hard problems. Okay, so they can solve their own class of problems known as BQP, and there's perhaps an intersection of BQP and something in between P and NP, but generally NP hard problems are not meant to be solvable on a quantum computer.
Thanks, Garnet. That was a really nice talk.
Oh, hi, Mark.
Hi. So, if you want to simulate processes in chemistry or, certain areas of physics where you've got diffusion and there could be strong nuclear quantum effects, you're probably not going to turn to the wave function. You're going to turn to the path integral, possibly coupled with the electronic Schrödinger equation so you can get the potential on the fly or whatever it is you're doing. But I'm wondering, how do you see these two worlds coming together? Because at the end of the day, first of all, I haven't seen really anything about quantum computers for path integrals, whether thermal or dynamic. But I could say, for example, my quantum computer runs, it gives me the wave function, the ground state, and then I use that, I get the potential, I do something with the path integral, go back to the quantum computer, it gives me the next, the realization of the potential for the new thing. Or do you think that, at the end of the day, I could do everything with the wave function if I have a powerful quantum computer? So, where do you see this all coming together?
Well, I don't, it's very hard to know, right? But, so I'll just say some random things that are related, right? So I think, formally, if you just simulate the dynamics of the nuclei and the electrons together, you don't have to get the potential energy surface. And that dynamical problem is formally polynomial cost on a quantum computer. And so, if you had quantum computer with very fast gate speeds, and you just do that, right? But in practice, the prefactor is actually very large, and so maybe you would want to go via the Born-Oppenheimer approximation for that reason. The second thing is like about path. So path integrals are like a sort of representation of quantum mechanics where you can start to classically sample. And I think, one would usually argue that in a quantum computer, there's no problem storing the whole state. So why sample it? Right? So I think that's why one doesn't discuss the path integral so much. But who knows? I mean, there are many. It's hard to predict these things.
Yeah.
Thank you. You made it very clear how important it is to properly prepare the initial state in order to have the correct answer to your question.
Yes.
Then you also mentioned a very interesting problem of chemical affinity in drug research.
Yeah.
Can you perhaps be a little bit more explicit on how you would prepare the initial state for such a problem? Let's make it simple. Let's suppose that I have a simple molecule, a sugar molecule, and I want to know what is the affinity of this sugar molecule to some other molecule. How would I prepare my initial state?
Yeah, so again, there's like different bits, but roughly, so let's just start from the end, right? So compute the affinity of something. What you do is you compute 3 energies. So you compute the ground state of the molecule and the protein, and then you compute the ground state of the protein, and you compute the ground state of the molecule, and you take the ground state of the aggregate and subtract the energies of the ground state of the individual pieces. So the affinity or the binding energy is just obtained by adding and subtracting 3 ground state energies. But to prepare the initial ground state of a molecule in principle, there's many procedures, and one procedure is to say let's turn all the interactions, all the complicated interactions between the particles off, and so you have some almost analytically solvable problem, and you can basically write down the answer, and from that answer you write down based on a piece of paper, you can dial the knobs of the quantum computer to prepare that very simple state. And then you can try and slowly change that state so it looks a little bit more like the ground state. So the idea is that there is some very simple solvable problem nearby whose ground state looks a little bit like your ground state is like one common way in which you might think of preparing a state.
It's awkward. Thank you, I appreciate that. I just want to make, this might be more technical than it's worth, but when you're talking about NP-hard problems, all NP-hard problems are isomorphic to an Ising Hamiltonian, and adiabatic computers do solve that. The fly in the ointment is the adiabatic time constant is exponential in the number of particles, but it's at least within the range, so if one can think of these clever algorithms, I wouldn't want to take the NP-hard problems off of the quantum map yet. Just a minor comment on something you said.
Yeah. I mean, one can solve NP-hard problems. It's just a question of whether you expect to move them into the polynomial complexity class. I mean, one can of course try and solve NP-hard problems of some finite size, and that's commonly what one does with classical computers all the time. And quantum computers may indeed be useful for that. Yeah. But yeah.
That you delineated between classical and quantum computers and some advantages for quantum computers where you can store in n-particle, n-bit kind of systems. Why don't we treat them more like accelerators? Like, can they be interfaced, the two of them, to bring the heuristic advantage of classical computers with the storage capabilities of quantum computers?
Yes, of course. One can imagine, so the question was, can you imagine combining quantum and classical computers? And of course, yes, right? And then the second question is, you mentioned the word heuristics. And for example, if you have quantum computers around, nowadays a lot of quantum computer science is purely theoretical, right? You try and design things without any hardware. It's very strange, kind of thing to do as a computational scientist. But if you had quantum computers all around, you would come up with quantum heuristics, and that may be some important field in the future. So yeah, so indeed, you can imagine combining them.
Hi, yeah, thanks for the great talk. I was wondering if you can comment on the role of ground state problems versus dynamics problems. So something I've always found kind of funny is, as you mentioned in your talk, it's maybe harder to expect generic speedups for ground state problems from quantum computers. But from the perspective of trying to solve, real world problems, when do you expect dynamics problems to be the thing that you really want to solve? Because in practice, things don't always evolve to their ground state.
Yeah, right. So the question is, in this talk and indeed in many times, one seems to focus in the physical sciences, one's focusing on these ground states and so on, but everything in the world is, dynamics is important and so on and so forth, right? So, yeah, so that sort of comes to sort of the last kind of slides that I was talking about. So if we had like perfect quantum control of experiments, then I think quantum dynamics would be a much bigger part of our vocabulary. But the way in which much ordinary science is done is you just do something and then you observe it after it's settled down, and you don't really follow the path of the dynamics. And in fact, usually you do experiments under very noisy conditions, right? And so for the experiment to even make sense, for even to be reproducible between one lab here and another lab, the quantities you observe have to, in some sense, be very ignorant of the precise dynamics or very insensitive to it. Okay, so because we measure things in such a simple way, our vocabulary is very biased towards just equilibrium ground states, and that presumably will change, over some period of time. Though my guess is quite a long time, but I think, 300 years from now, perhaps everything will be all about precise readout, precise quantum control, and we'll use quantum computers for everything.
Thanks.